Hi, this is Dr. S.P. Harsa from Mechanical and Engineering Department, IIT Roorkee. In the course of vibration control, we are discussing about the principles of active vibration control, in which we discussed about that how you see what the basic principles of the active vibration controls are, in which you see we can sense, we can actuate, and we can put the control unit through which we can amplify the things, so we can put some kind of external source to actuate and to balance the whatever the excitation forces are. Then we discussed about the smart materials under the active vibration controls, right from piezoelectric materials, that how these piezo sensing and piezo actuations can be acted for active vibration control. And also we discussed about in the under this category about the electrorheological fluid. The ER fluids they can exhibit a kind of damping features through which, and also you see along with that we can put in the actuation part, so that they can be acted effective, we can say, way to control the vibration. And also you see in previous class we discussed about the MR fluid, the magnetorheological fluid, that how you see when we are applying this the magnetic field or the flux, you see here all along you see these particles which are being there in the carrier oil like silicon oil or any non-conductive oil, then they can put by adding the magnetic field there is a clear addition of the viscosity, and they can be just align according to the direction of the fields, or you see, and it is just we can say that if it is perpendicular to the applied field part, and they are straight you see resisting that whatever the kind of vibrations are there. They can absorb the vibration, excitation energy, or the dissipation features can be acted. So we discussed about the three main modes in that. One was the flow mode, one was the shear mode, and in these you see here in all, and one was the squeezed mode, squeeze mode, and in all three modes they are absolutely acted according to the kind of applications. So if we want to see just for normal operations in which the vibration controls are being there for the beam or something, the flow mode, or we can say sometimes it is a wall mode, is quite effective. Even the shear mode is also very effective in such cases. Then in these magnetorheological fluids we discussed about that how we can simply locate the the potential location where these fluids can be placed, and we can get an effective vibration we can say suppression part there itself. So you see here in last two lectures it was mainly focused on the electric field with the the particles which are being arranged, and they are just putting with the additive viscosity part, and also you see here when the magnetic fields are being acted, and these things are there, and these all resistances are being provided by the fluids. So the entire part was there, surrounding with these fields and the conducting oils, the non-conducting oils with the carrier part particular. In this lecture now we are going to discuss about the similar feature, like if we have the magneto or the electrostrictive materials. What does it means that you see here? We are saying that both the magnetostrictive and the electrostrictive materials demonstrate a shape change upon the application of these fields, the magnetic or the electric fields, and the shape change application is very sensitive to the we can say the capacity or the intensity of these fields are the magnetic or electric fields. So the small change is believed to be caused by the alignment of these material, we can say magnetic or electrical domains within the material upon the application of these fields. And the advent of the the specialized engineering material which enables the use of these material in active vibration control application, just because of the increased deformation strains. So that is why you see here when the change in the shape or the strains are there, correspondingly we can simply judge that how much you see these we can say suppression of the energy or some kind of the this force applications are there on that part. So when we are talking first about the magnetostrictive materials, it started from you see say the James Prescott Joule first discovered the phenomena of the magnetostrictive effect, means the Joule effect we can say, and defined the concept of this magnetostrictions in 1842. So this magnetostrictive material, they are simply changing their shape when it is being subjected under the magnetic field, just like you see here, we simply see that there is always humming noise is there, this humming noise is there, which is being emitted all the time under this from this electric transformers, and this is due to the expansion and the contraction of the metallic parts in response to these magnetostrictions, which is being induced by the change of electromagnetic field. So, this like every time when there is a change in the electromagnetic field, there is a clear change in the shape, either like the contraction or the expansion, and because of these like thing, there is a clear response against these kind of, we can say, the changing of this field, and we are simply getting a kind of humming noise. So, this is a perfect example of these magnetostrictive actions on that. As you can see on your screen, you will find that we have like the randomly oriented these magnetic field. So, you see like when we are saying that these randomly oriented, you can see all the directions about these like the atoms together, and when we are trying to apply like these what we can say this magnetic field, then you can see that the entire material is just, you see, either the like we can say expanded or the contraction. So, here we are simply showing the expanded part, this is what my like the strain part, and when they align along with the direction of the magnetic field, you can see that there is a clear expansion feature is there. So, here there is only change when we are simply applying the magnetic field, and because of this application, you see all the particles along the layer, you see here they are simply streamlined, and because of that, you see here there is a clear change in the dimension. And again you see here this change, the strain part is absolutely depending on the flux intensity, that how much like these electromagnetic forces are being generated, and because of that, you see here there is a clear change in that. So, the most popular and simple model to explain the behavior of this magnetostriction is simply a ellipsoid model. As you can see that, as I simply shown you that like when they are randomly oriented, means there is no like the electromagnetic magnetic fields are there, the H equals to 0. All the ellipsoid material, they are randomly oriented, and you see here the direction even itself is just varying like this. And when you see the magnetic field which is being applied in this direction, you can see the H direction, all these ellipsoid molecules, they are being arranged, and because of that we have a clear strain or clear extension feature. So, magnetic domains are being represented by the ellipsoid with the magnetization direction pointing along the major or minor axis of these ellipse, and corresponding, you see here when they are simply aligned, there is, you see here like we have clear whether they are lying vertical or horizontal, there is a clear, you see, expansion, or we can say the contractions are there. So, you can see here that when we do not have any pre-stress, these things are being even like you can see that they are being arranged in this way. And when you see like the pre-stress are just like you see these pre-stresses are being applied there, just you see like just to put in a compact way, then you can simply see even under like this what I mean to say this the magnetic field, they are straight way you see being arranged in this particular part. So, the pre-stress is clearly causing the change in the direction even in the presence of, we can say, the magnetic field, and in this case you see here there is a clear change. You see here when the pre-stress is there, the change is even more significant along the major axis. So, when we do not have any pre-stress, you see that the magnetic field can generate, you see, the expansion certainly, and this expansion can be like encountered with respect to like this strain part, that is nothing but equals to change in length divided by the original length. But when the pre-stress is there, that means all the these ellipsoid elements, they are absolutely in the robust contact, and when we now apply the magnetic field, the expansion is even quite more. So, you see this is what you see the expansion size, and we have the strain which is quite significant as compared to the without pre-stress concept, and we have, you see, delta L by L. So, under external magnetic field, the ellipsoid rotate, and because of this rotation there is a clear change in the dimension. So, the ellipsoid model also can be used to explain the effect of pre-stress as we discussed here, And in this we simply got that when the pre-stress is being applied, or when we have a preloading feature, because of that some stress phenomena is there in the material side, we know that whatever the rotation is there, they are being away from the stress direction. And then you see when we are just trying to apply the magnetic field in the direction of these applied stresses, or the applied force rather we can say, the resulting restriction action will be larger, and then you see there is a clear cause of more extension than the without pre-stress concepts. So, we can say that these magnetostrictive materials, they are almost, you see, nearly all ferromagnetic material demonstrate these kind of property, but the shape and the volume change is very small in ferromagnetic as compared to the magnetostrictive materials, because these ferromagnetic materials have the structure divided into magnetic domains which can exhibit the uniform magnetic polarization. And this is what you see just bifurcating the ferromagnetic material from the magnetostrictive material. And when the applied magnetic field causes the rotation of these domains, then in return a slight shape change in there at the macroscopic level. So, that is why you see somewhat different feature is there in that. And when we just want to see the deformation in these magnetostrictive material, then we can simply characterize this with the magnetostrictive coefficient, which is straightway you see coming from the fractional length change when we are applying these things. So, we can say L MS means the magnetostrictive part or something. But mainly you see here when the shape change of the material is 0 at 0 magnetic field, we can say that the application of these flux on the expansion or on the orientation of these ellipsoid particles, it just grows linearly according to the magnetostrictive coefficient until the material reaches up to the magnetostrictive saturation part. So, you see here in this it is a clear feature that you see here it has to reach up to saturation, and beyond that even we are giving the strength to our magnetic flux, there will not be an effect, means the H, we are increasing the H, but there will not be any effect in the contraction or the expansion of these materials. So, the mechanism of these magnetostrictions at an atomic level is somewhat more complex, because you see here at the macroscopic level we need to segregate this entire concept into two main features. One in which you see these processes are being dominated by the migration of these domain walls within material in response to the external magnetic fields. So, we need to see that what kind of migrations are being taken place at the macroscopic level of atomic part when you see we are simply applying the magnetic field from outside. And second, we need to see the rotation of the domains, because we know that you see here there is a clear rotation of the domains are there in which you see the molecules are being rotating towards that. So, these two mechanisms in which one is the migration feature of the domain and one is the rotation feature of the domain allow the material to change the domain orientation, and because of that you see here there is a clear cause of dimensional change. So, we can justify the change in the shape of the domain either by the migration feature of the entire domain or by rotational feature of the domain. And since the deformation is isochoric and there is we can say the opposite dimensional change is simply we can say the orthogonal in the orthogonal direction, because it is always being there you see here when we are applying you see the entire magnetic field in the uniform environment, then whatever the changes are there in the spatial we can say the deforming feature, it is always being there in the orthogonal direction. And even you see when it is being reoriented, there are various mechanisms in which we are simply explaining that how the reorientation of the domains are. But here you see our main feature is to just give a clear understanding about that how the rotation and the movement of these magnetic domains are being there, through which there is a clear cause of the change of the physical we can say the dimension changing in the entire material. because we know that these magnetic domains are always like influencing the shape of the material. So that is why you see like even for this disorientation or the reorientation part, means when the magnetic field is being applied or when it is recovering part, there is a clear like we can say these rotation, or we can say the displacement, means the migration features are there of these domains, and we need to see that how this mechanism is working. So we now you see we are taking that when these materials are being there under, we can say like the normal operation, and a compressive load is being applied to the material, which is due to, we can say, the magneto-elastic coupling forces. And you see we can say when it is being magneto-elastic coupling, whatever the forces which are being there in the like in the entire structure domain, certainly being like there, they are acting perpendicular to the domain of these applied forces, or we can say like whatever the main domain is there. So a magnetic field is introduced in this, and the domain structure rotates and producing the maximum possible strain in the material. So a tensile preload should orient the domain just like we can say parallel to the structure, and whatever the applied force is there, through which we can say that we cannot get, you see like the kind of the maximum strain in this. So we can say that you see the brittleness, or you see like whatever you see the main property makes this material more comfortable in the compression part, and through which we can say that we can generate maximum strain in these material rather than in the tension feature. As you can see here, this is clearly showing that when you have like these orientation, the stresses are being like this, and when like we are just making the compression, the first is showing you see the compression part, you see, and when the compressions are there is a clear you see like the changes features are there. But when you see like even in both the cases, you see this is a well you see the compression, and whatever you see like these shape changes are there, they are quite significant in these cases. But when we are applying you see the tensile feature, because of the brittle nature of the entire fibers or the material itself, they are not exhibiting a maximum, we can say the strain feature in this. And in these cases you see here, you can clearly see that whether the orientation of these like the particles are like that, or the orientation of these particles, the ellipsoid or anything you see are these, we can get you see the maximum extension feature under this magnetic field part. So if you are just going with the basic principles, now you see here this is what my like the magnetic field which is being there, either we can say the AC or the DC part, you see these are the two clear features which are being showing. The AC stray magnetic induction, which is BC, like B under this subscript BC, and you see when it is just like targeting to the eddy current loops, these are all my eddy current loops, you can see that, which is clearly like based on what the density part is there in the electrodes. And because of this you see then the Lorentz forces in the like we can say electrode transfer to the piezoelectric features. By this formula we can say whatever the force, the Lorentz force dF, just at the segment, the dF is equals to J, that is nothing but the density of the current you see, into B this BAC plus BDC into d tau. So we can say that this like this is being supplied, the static magnetic induction, we can say BDC. And when you see when we have the Lorentz force with like with these the electronic feature, we can clearly exhibit an efficient mechanical and energy like the this conversations you see, means using the exchange part right from the mechanical energy to the electric energy along with these Lorentz forces can be efficiently exchanged. And when the things are being there, we can have a good output in terms of you see the piezoelectric part, and that can be like create the magnetic field sensor, or we can say the magnetic energy transfer features are being there. So both the things, whether we are talking about you see the magnetic field we can say like the sensor part, or like it is being dissipated part, it can be immediately like done by these piezo features of the entire. So this is what you see the basic principle in which it is being like working at the microstructure level, when the magnetic fields are being applied there, then how you see the entire molecules are being worked, and the Lorentz force which is being generated due to these, they can be immediately like transfer this in efficient way from mechanical to electric conversion. So, you see here now in this particular diagram, it is a clear like we can say feature, it is a clear feature which is being exhibited there in terms of you see the magnetic force H, through which we can say that it is a clear change in the dimensional feature due to alignment of these magnetic domains. So, we have you see this part, if you look at this clear, we have you see this is like the alignment of the molecules there itself, when there is you see like, and then these are the different orientation, one is going like this, one is going like that, and these all different orientations are there. And you see the size of this entire is this L, say. When the magnetic field is being applied, say this one, the H, in this direction, all these molecules are being like this we can say oriented towards you see whatever this magnetic field is being directed, and then we have even the physical change in the entire parameter. So, this is you see like that is what we discussed, that you see these Lorentz force which are being there between these, they are straightway directed towards you see whatever like these mechanical parts are there along with you see these molecules. So, the physical response of the ferromagnetic material is due to the presence of these magnetic moments, and then you see we can say that it is all you see like with consideration of all the material, there is a clear collection of these tiny permanent magnets, or we can say rather they are the domains. And when the material is being magnetized, the domains are oriented with their axes approximately parallel to each other. Though you see right now we are showing through this diagram that they are absolutely aligned, but sometimes you see according to the intensity and the effect on the structure, microstructure, they are approximately you see aligned and parallel to each other. And the interaction of these external magnetic field with the domain is clearly causing this magnetostrictive effect there. So, you see like we can use these ferromagnetic material and these materials as the sensor, which are like which are in the transition metals such as the iron, nickel or cobalt, that can be like the base materials are there, and in these metals the 3D electron cell is not completely filled. Since they are like all these 3D element, they are not filled, they are allowing the formation of the magnetic moment within this empty field. That means you see the shell which is closer to the nucleus than the 3D cell which are being complete, they are simply like if they are being complete, then certainly they will not contribute in the magnetic moment, but whatever the empty features are there, they will certainly cause the magnetic moment and they contribute in that. So, as the electron spins and they are being rotated you see by this magnetic field, a coupling between the electron spin and the electron orbit in the empty space, these spaces are certainly causing the electron energies to be changed, and then you see here these changes of the energy is clearly like showing by the exchange feature, and since we are applying the magnetic field through which you see there is a clear change, means whatever you see we are causing the stresses, that through this you see there is a clear change in the physical property of the magnetostrictive material. So, we need to see that, say if we are just going in reverse way, means you see here when we are applying the stress to the magnetostrictive material, and we need to see the changes in its like the magnetic properties like the permeability or other things, we can say we can see that what the reverse effect is there, and this effect is sometimes is calling the this Villari effect. So, the application of certain rare earth material into the alloy allowed using this effect of magnetostriction in the real life engineering application is really significant. So, we can say that they can even these alloys can demonstrate the large magnetostrictions, but again you see here when we want to exhibit such things, we need to apply the huge amount of the magnetic fields, or we can say we need to apply some kind of the cryogenic temperatures on that, then only we can see the feasibility of that. So, you see here when we want to see these things, we can simply remove these difficulties by introducing the Teflon D6, which is like we can say a continuous common type of the magnetostrictive material. So, Teflon D is always being exhibiting almost up to 2000 micron like the strain at the room temperature, while we can say the cobalt, which can demonstrate even large magnetostrictive effect of a pure elements, and they can exhibit almost up to 60 micro strain. So, you see here like we can exhibit right from 60 microns, we can say the shape change in the cobalt to 2000 microns shape change in the Teraflon D6. So, you can see that what we have a clear this say Teraflon D drive mode is there, that means it is here, and then you see these like the coils are there through which we can straightway put together the part, and then these are like the permanent these magnets are there. This is what you see the preloading part, because we know that if we want a significant deformation or the shape change, certainly the preloading springs are always being required, and this is my output. So, when we are looking towards the piezoelectric feature, then these are like the we can say the arrangement of these our molecules, and in these you see whatever the empty spaces are there under the action of these magnetic field, there is a clear cause of the magnetic moment, and because of that you see here with the electron spin and with these like whatever the rotations, they are simply causing whatever the electric energies which are being changing into that the shape part you see. So, you see like these magnetostrictive materials which are clearly showing here that when we are applying, you see this is what you see the alignment, when we are applying the load means the magnetic field, there is a clear change in the length when they are being applied in such a way that. So, this is what my delta L, and then I can get like that what exactly the strain part is there. So, this is the straight this Teraflon D rods are there that can be straightway put here, and we can see a clear change even at the micro strain or at even this one. So, you see even at the micro strain or the real structure, this is what the things are being happening when like the entire lattice structure is being strained according to the magnetic field is being applied there. So, a typical this recoverable strain of the magnetostrictive material, just like for this Teraflon D, is in the order of almost 0.15% only, and the maximum response is presented under the compressive load is always being there because of the brittleness. So, they are quite insensitive towards like the tensile feature, and these magnetostrictive actuators have long lifespan, and that can be used in like for high precision applications. So, actuators which may be used in compression along with the load carrying elements are the perfect featured for these kind of materials, and in this the pre-stretching these actuators can also increase the efficiency and the coupling effect for these actuation features. So, we can say that these materials which have this anisotropic feature in the opposite direction, that can be straightway like shown either with the cobalt to we can say this Teraflon D, because these material have a tremendous magnetic anisotropic feature, and certainly it is required because a very large magnetic field is certainly required to drive these magnetostriction features. So, we can say that when the anisotropic feature is there, so the recovery part is almost here irreversible like as compared to whatever the extension features are there. So, these we can say like the alloys are generally stoichiometry of the form of TBX dy1 minus x Fe2. So, like that can be coined with the Teraflon D, which is operating under like the mechanical bias or the strain can be produced in the field of like the 2 KOE at the room temperature. So, we can use these like the Teraflon D as a transducer or the actuator for many of the application where we need the accuracy features. So, you can see that this is what my actuator part is there, where the Teraflon D is absolutely there in this middle, and you see here we are absolutely applying the this is like this spring for pre-stressed part, and then you see through this load shell, and you see like these whatever the AC drive cell, now like the field is being created and it can be straightway actuated towards that. So, we have a clear actuation feature there itself, and this is almost in this particular arrangement we can say that we can get in the actuation of the entire lever system which is being there on top of that up to almost 0.8 meter. Because due to processing character of the simple structure, it is clear easy in installation, as you can see that, and we can get, you see, the steady performance. They can also be acted as the friction damper, because you see here when we are changing, the orientation, they have, you see, like the gap from where you see the magnetic moments are being created. So, the energy can be straightway put there itself. So, they can act as a friction damper towards that part. So, as its performance cannot be changed during the utilization, you see, and the part, so we can say that the frictional damper can be adopted there itself at the structure where the vibration features are quite significant. So, utilizing as the actuator made by this magnetostatic material, we need to adjust the normal force of the friction damper, and then we can say that we can rather change its frictional forces, which is something you see always adjustable because of the simplicity feature in manufacturing of these magnetostrictive materials. So, this is the uniqueness you see here. They can be acted as the actuator part, they can be acted as the, we can say, the damper part, through which we can straightway suppress the we can say vibration up to, you see, the low frequency part. The second is coming as the electrostrictive material. The electrostriction is closely related to these magnetostriction, but due to this electrostriction, all the dielectrics changes their shapes upon the application of the electric field only. So, we have, you see, the dielectric we can say, these features are there with the elements, and they are changing their shape when we are applying the electric field on the particular this specimen. The physical effect is similar to the same magnetostriction, where we can say that the non-conductive materials have randomly aligned polarized electric domains. That means, you see, now we have a polarized feature with the electrical domain part in the particles, and then you see here when we are applying, and even it is a non-conductive material, and when we are applying, you see, these electric features, then certainly you see here there is a since outside there is a strong electric field, and the opposite sides of these domain becomes now charged with the different polarity. So, domains will be the domains which are being attracted by each other, we can say that it is absolutely reducing the thickness of the material in the direction of the applied field, because we are simply elongating the entire, we say, the domains in a particular direction where the field are being applied, and you see there is a clear extension, but the thickness is, because you see here they are being randomly oriented. So, their thickness is being quite increased, but when they are being aligned along with the applied strong electric field, the entire elements are being we can say just approximately parallel to each other, and all the dielectrics can exhibit the same level of electrostriction, and we can say that you see whatever the engineering ceramics or you see the various features are there in the ceramic part can produce the higher strain than any other materials or the polymers, and such materials which are exhibiting such we can say the electrostriction feature, we can say they are somewhat the lead magnesium nibode, means PMN, or you see the lead magnesium nibode lead titanium, because we need to, when we are adding the lead titanium, the additional features which can exhibit the strong part of the electrostriction part can be exhibited, or and also we can use the lead titanium zirconate we can say the lead lanthanum zirconate titanium, the PLZT, that can also be used as the electrostrictive material, because we know that when these ceramics which are producing the high strain, even these materials can be known as the relax or the ferroelectric parts there itself. So, in this the elongation which is being there under the application of this electric field of these electrostatic material can be explained by the strain is equals to one constant into E square. So, here you see whatever the strain which is being producing, we can say that it is showing highly sensitive feature with the nonlinear impact of this electric field strength. So, we can say that when the relative percentile elongation changes are there in PMNPT, PMNPT is nothing but equals to the lead magnesium nibonate with PT means the lead to titanium. So when this PMN PT is being using now, and we just want to see the percentile changes when the electric field is being applied, we can say it can be right from 0.1% to, or we can say it is almost going up to the 1000 microstrain, and can be achieved, you see here, this much you see the strain when the field strength is of 2 megavolt per meter. So you see it is always being causing some kind of like the electrostrict strain part is almost 0.02 to 0.08%. So you can see that this is what you see this greenish area is clearly showing the electrostrictive areas when they are being under these like the field part. So this is what my electric fields are being applied in all three cases, and when you see we are going with the different profiles, then you see that we have a clear variation in the sizes of the electrostrictive areas. So when you see the electric field and these this WT profile is there, we have a clear variation in this direction, and when we have the LT profile there itself, then certainly you see here it is a clear extension part, and when we are simply applying you see the LW profile, then certainly we have this kind of features in which you see there is a clear the compression part at the particular we can say electrostatic area, but outside you see here this is a clear, we can say these features are there, the compressive part. So in all we can say there is a clear change in the we can say the strains are there, as we can simply see the whatever the profiles are being concerned with the electrostrictive areas. So now you see here when these materials in which you see we have both the magnetostrictive and you see here the electrostrictive concepts are there, we can see that there is a clear change in their properties, means towards we can say the deformation or the shape change when the the fields are being applied, and they can be simply act as the actuation feature rather, and also sometimes they can be acted as the damper part. So magnetostriction is nothing but you see, as we discussed, the changing of materials physical dimension with respect to the whatever the magneto fields are being there, or we can say this is magnetizations. Or in other words we can say that a magnetostrictive material will certainly change its shape when it is being there under whatever the magnetic fields are there. So you see, as we discussed, you see lots of like the cobalt to the terephthalate D, they can be straightway shows this kind of you see like this particular part, and sometimes you see we can say that one which is being achieved, the giant magnetostrictive under relatively small field, we can say this is like one of the specific part which can be used as you see the vibration control feature. So now we are just talking about the vibration control, we can say a mechanically amplified these MS, the magnetostrictive actuator for low frequency just 1 to 10 hertz. A vibration damping application is absolutely featured out from this, where we can achieve you see the displacement is almost rated between 0.5 to 4 millimeter, and we can even apply you see the force of certain kilonewton, 6 kilonewtons. So we can say that lots of these MS actuators are being available which can deliver the high force output with the high frequencies also. So either whether we are going with the electrical, mechanical or any this magnetic phenomena, we can simply use you see this concept, the MS actuator, but we need to understand this with the using of the nonlinear hysteresis behavior of the terephthalate D, because we know that you see when they are being loading or unloading conditions are there, there is a clear loss is there, and this loss is not the linear, this is the nonlinear feature. But when you see when we are like trying to set up the relation, we can simply assume the linear property of the MS actuator, and it can only be hold when we are assuming the low driving frequency of the entire system, whatever the exciting frequencies are there, then we need to assume that there is a clear reversible magnetostriction featured are there without having any power loss. When you see when we are just adopting the loading and unloading features, and then it needs to show, that is what you see we are assuming the uniform stress and strain distribution, And when such things can be achieved, then we can say that there are two main equations which can be clearly relating the magnetic field, whatever you see the frictional features there itself, and then you see here the this we can say how these stress and strains are being there. So, it is S equals to SH sigma plus G HM, that is one. Second is BM equals to Z sigma mu into HM, where we are saying that the S is nothing but the strain, and we are trying to see the strain is nothing but equals to the stress into SH. SH is nothing but you see a constant which makes you see like the compliance feature, means we have you see what the compliance part is there when we are applying a constant magnetic field strength H. So, this is one part SH into sigma, plus we have the G, which is nothing but the coupling part, and this magnetic cross coupling coefficient is always being there, that how like it is being attracted at the interfacing part, and into H is nothing but equals to my what the magnetic field strength. So, the first equation is clearly making the relation between the magnetic field strength to the stresses with these two coefficients. And second, you see here the equation which clearly exhibit that what is the magnetic fluxes are there within the material is nothing but equals to the cross coupling feature into the stress, means how like the cross couplings are there, and then how the stresses are being generated within the molecule feature, plus mu into HM. HM is my magnetic field strength and mu is the magnetic permeability, that is the inherent property, the material property, which always we are considering that when the constant stresses are there, the mu into sigma constant stresses are there, we can simply get the magnetic permeability feature of the magnets. So, in this you see here we can say when the things are being happening, the piezoelectricity is being featured out, which is in fact you see a subclass of these electrostatic materials. And when you see these electrostatic materials are nonlinear, these PZT materials, piezoelectric materials behave linearly, and then we can say that we can straightway apply this feature for the control applications. And also you see this electrostructive like concept is not a reversible effect, as just like you see the magnet restrictions, or even we can say like just like we have seen that this piezoelectricity is there, in which you see the material is always going in a linear formation. So, we can say that the material which does not like go under the deformation when the electric field is being applied, we can say it is some kind of you see the restriction provided by this material against this one. And also this electrostatic material, they do not reverse the direction of the elongation when we are reversing the electric field. So, when we like stronger, when we apply the strong electric field and when the entire orientation is there, we have the extension feature in these materials. But when we are decreasing and when we are even going like towards the reversing feature of the electric field, it is not going in the compression part. So, you see here the reverse effect is not at all there itself. So, we can say that you see when we want to design like the controlling feature, we can go up to 2 kilohertz frequency range to control that. And you see here we can say that we can straightway apply in some of the experimental features for an inertial type of MS actuators, through which we can at least control, or we can say like actuate the things. And since we know that the linearization is not the feature for these magnetostrictive or the electrostatic materials, but you see like when we are adopting you see the traditional feedback control system, we can at least you see like trying to reduce the error of whatever you see like the desired and the actual outputs are there, and we can try to like make proper control on this. So, now like we can say that we can straightway adopted this MS actuator, but the main thing is that we need to couple with the hysteresis and the nonlinearity effect when we are actually adopting this actuation feature or actuation displacement from this MS actuators, because we know that the MS actuator is clearly showing the linear actuations. So, when we are trying to make this with the actual part, we need to couple this thing with the hysteresis loss and the nonlinearity feature in this. So, you see like the Lee et al. Lee and like their associates, they simply exhibit the behavior of this MS actuator in one of the composite shell experiment. And even you see the few of the the behavior, few of the experiments have been done by the Pradhan, and they were simply showing that what exactly the vibration suppressions are there in their own composite shell when they are using the magnetostrictive layers in these shells, and through that you see here there is a clear suppression of the vibrations. So they have framed you see the theoretical model for this this composite shell, and they simply showed that you see here there is a clear you see along with the this neutral plane, when these magnetostrictive layer, when they are simply putting in such a way that they are just away from this, the this MS layer can produce a good damping feature there itself. And MS actuator, which is based on this this vibration damper part of the simply supported beam, is also discussed by the Moon. And in his work you see he simply showed various experimental setup through which he simply showed that there is a clear significant change in the the reduction in the vibration, especially in the in the comparison of these other materials with this with we can say the scenario without having this control. That means there is a clear effective control is there in the beam part when the layers are being adjust with these magnetostrictive layers part. So these the composites are clearly showing the vibration absorber feature in that. So we can say the sonar projectors are the typical field for the use of this electrostrictive actuators, in which you see the vibration attenuation rather than the generation of the acoustic wave is a significant part. So you see the lots of work has been done in these cases, and they are simply showing that you see here whether the magnetostrictive or the electrostrictive material, they can be successfully applied in the damping as well as in the actuation part together. And then you see here whatever the the kind of say even for low frequency vibration, or even we can say you see whatever the forces are being generated through actuation, it can be even amplified with this. So as you can see on the screen, we have the miniature MS actuator, and these actuators are are in the any of the forms according to you see what kind of the applications are there, where you see the field and the load applications are required. And then you see it can be solved using the finite element method, even they can be mathematically formulated. The experimentation can be done using these magnetostrictive or the electrostatic material layers composite feature, and then can be performed to see that how much vibration suppressions are there or how much actuations can be formed from these parts. So in this lecture you see here this still the research is much of the research is going on, and the materials are being framing not only with the ceramics part, but also now you see they are simply checking with whether it can be framed in the polymers and then it can be acted like that or not. So you see this composite kind of structure with the magnetic and the electric field, the magnetostrictions and electrostrictions this concept can be explained, and you see can be framed into the real materials which have been which is being there you see in the recent time. So this is all about this the magnetostrictive and the electrostrictive materials, how they can exhibit, what the concepts are there, and then you see here how we can use for especially the vibration suppressions. So in the next lecture now we are going to discuss about the new type of material, this which is also coming under the category of the smart materials, named as the shape memory alloys. In this you see here we are going to see that how the shape changes are there. As we know that you see even if we are applying you see any electric or magnetic field, there is the polarized molecules are there, and accordingly they can be rearranged themselves and can get you see the shape changes. But the name itself speaks that the shape memory, that means you see here these materials have their they can memorize themselves pre and post effect of these part. Means you see pre and post applications, they can be rephrased or reframed themselves into their original shape. So you see the shape memory concept and the shape memory alloys materials are going to be discussed in the next class. Thank you.